So, in the last class, we had a discussion about this temperature. Just a second. Yeah. Yeah. So, uh, in the last class, we had discussed about this temperature independent reference circuit. Okay. So, we were more specific about generating this voltage, and we had began with the discussion about this reference circuit, and we said that this reference circuit is a circuit that generates a constant quantity, say for example a voltage, okay, irrespective of any changes in temperature or changes in process parameters. Okay, so irrespective of any of these variations, they tend to have the same voltage. And before this reference circuit, we had a discussion about what is known as biasing circuit, where this biasing circuit has a different type of output. Uh, to be specific, it can generate voltage or a current, but those voltages tend to be a variable one. Okay, so it is not like a constant that has been generated out of this reference circuit. They tend to have a variation, and these variations depends on the changes in the process parameter. Okay, so these variations depends on the process parameter or variations in process parameters. Okay, so this is something I'm just trying to recall what we have discussed before. But as we know that this reference circuit in general has to generate a constant voltage. Now, in order to have this constant voltage, we actually postulated something like if there exist two quantities like voltages. Okay, so in this case, I'm just assuming that we have voltages as our quantity, uh, where both these voltages have opposite temperature coefficients. Then what we can do is that we can sum those two quantities with appropriate weights to yield a resultant voltage. Okay, this resultant voltage will then be completely independent of temperature, or will exhibit something known as zero temperature coefficient. Okay, so this is a statement or the postulate that we discussed in the last session. And let me draw this, or let me characterize the statement graphically. Okay, so let me just state what you have written through graphical quantity. So, say for example, I have a voltage V1, which is one among the two voltages, and if this voltage exhibits a Cara whose first order differentiation with respect to temperature, or just nothing but the slope of this particular Cara, if it turns out to be a negative value, then we say that this particular Cara exhibits what is known as negative temperature coefficient, and the circuit that provides us this kind of negative temperature coefficient is called as complementary to absolute temperature circuit. Okay, the circuit that has this Cara, right? And so this is one such voltage that we have. Then the second voltage that we need in order to create a reference voltage should have an opposite transfer Cara. Okay, let me take the second voltage as V2, and that when we map with respect to a temperature, then that transfer function should exhibit this kind of Cara with a slope value, which is again defined as, or the temperature coefficient is defined as dou Vt, sorry, dou V2 with respect to temperature will then exhibit a negative value, okay, sorry, will exhibit a positive value. And so this is known as positive temperature coefficient, okay, just because when we differentiate this voltage V2 with respect temperature, it has a positive value, which means that we have a positive temperature coefficient here, okay. So with that being said, when we have such kind of characteristics graphs for both V1 and V2, then we can just combine them and then try to create a voltage reference which is completely independent of the temperature, okay. So mathematically one could write it as something like this, right. So mathematically what I really mean is that I just need to combine both these voltages such that if I take a weighing factor which is alpha 1, and when I multiply that with the negative temperature coefficient, okay, and that has to be added with a factor alpha 2 which is a different factor, and when I multiply with this temperature coefficient, the resultant quantity of these two quantities when they add up should end up having this result of 0, okay. So, in a way when we try to integrate this above expression with respect to temperature, so let me use a different color in order to distinguish. So integrating all these expressions with respect to temperature, and then even this when we try to integrate with respect to temperature, one would end up having a result after integration as something like alpha 1 times that of V1 plus alpha 2 times that of V2, and this integration of a 0 which results in a constant, right. So that constant is basically a voltage component and we call that as a V reference, okay. So in the last class we had a discussion about this V1, which is basically the here in this case I am assuming that the value of V1 or the temperature coefficient of this V1 is a negative quantity, okay. So this exhibits a negative temperature coefficient, and when we analyze the circuit that exhibits this kind of behavior, we found that the base emitter junction of a BJT structure, when it has been forward biased, okay, it exhibits basically a negative temperature coefficient, okay. So yeah, I think my pen has some issue in writing, yeah, okay. So this exhibits a negative temperature coefficient, and uh, this can not only be done across with respect to BJT, but even a forward biased diode, okay, a diode which when it is forward biased will also exhibit the same negative temperature coefficient, okay. So now for our discussion we will just make use of this BJT VBE potential in order to talk about this negative temperature coefficient, and I just want to write down only the final result of it just because we have already discussed all these terms. So when we analyze this VBE, the VBE or the temperature coefficient of this VBE potential gave us a result which is dou Vt, where Vt stands for thermal voltage with respect to temperature into ln of this Ic by Is, okay, and this Ic is nothing but the collector current, and Is stands for the saturation current minus Vt by Is into dou Is by dou T, okay. So this is the expression that we had, and let me mark this expression as equation number 1, and the final expression after doing all this derivation of Vt and Is, the final expression would end up having a value which is VBE minus 4 plus m Vt divided by Eg by Q, the whole of these things is being divided, okay. So yeah, so let me mark the second expression as equation number 2, so that we will use these references for our discussion, okay. Yeah, and one more thing, one more important thing is that I just want the equation number 2 to be made a note somewhere, so that we will be utilizing this equation later on when we discuss about this BGR circuit. Okay, so please ensure that you have written down this expression somewhere in your note. Clear? So with that being said, let me discuss about different terms that I have plugged in over here. The very first term that I just want to discuss is about this Vt, where Vt is defined as Kt by Q, where K stands for the Boltzmann constant, and I think its value is 1.38 in 10 to the power minus 23, and the Q value is nothing but the charge of the magnetic carrier. So in this case, we assume that it's the charge of the electron, okay, and T stands for the temperature. Okay. Yeah. So with that being said, the Vt is also called as thermal voltage, and here the term Eg, the Eg denotes the silicon or the band gap energy of silicon. Okay, and yeah, so apart from this, Is is nothing but the saturation current, which is again proportional to all different temperature terms which we discussed in the last class, and the final term is this factor M, and this M is basically approximately closer to a value of minus 3 by 2, and this is a temperature parameter term, or temperature yeah, so this is nothing but a temperature parameter which is related to the mobility, in a way that mobility of a charge carrier in short is proportional to mobility at the temperature of 0 Kelvin multiplied by a temperature term raised to the power of m, and it is this m is what is being written here, and what been expanded in this dou VBE with respect to dou T term. Okay, yeah. So we are not worried about all of these things, but the only thing that I am worried is this factor m, which is basically closer to a value of 3 by 2, okay, minus 3 by 2, and this is what we wanted out of this. Okay, yeah. So now here in the expression number 1, one could see that there are two kind of quantities, there is term A and term B, and among these two terms of A and B, the magnitude of term A is quite smaller than the magnitude of term B. Okay, so due to this magnitude relation, the final result of dou VBE with respect to dou T, we would end up having a negative value, and that is the reason why this VBE in short exhibits what is known as negative temperature coefficient. And for that, I stated that for a specific value, say for example, if the value of VBE or the nominal value of VBE is around 750 millivolt, and at room temperature where T is taken as 300 Kelvin, okay, the dou VBE with respect to dou T, in short, it approximately exhibits a value which is equal to minus 1.5 millivolt per Kelvin, and this is the statement that I made in the last class. And there were a few more observations that one could make out of this expression number 2. The first observation is that you could be able to see that uh, the negative temperature coefficient, which is dou VBE with respect to dou T, is a function of, is directly proportional to VBE, and also it is inversely proportional to the temperature. Now this relation basically results or yields a result which is, when it is plotted, where VBE with respect to temperature, if you want to plot this Cara, the Cara would exhibit some sort of parabola rather than a kind of graph we had before, which is a straight line. Okay, yeah. So we said that if at all, if this VB with respect to temperature exhibits this white line, which is the straight line, then the circuit that exhibits that Cara is said to be a CTAT generator, okay, or CTAT circuit. But right now we don't have the straight line, but rather it's a kind of curvature, which means that at every point with it's basically a function of both the value of VBE as well as it depends on the value of the temperature at which we are operating. Okay, so that is something that bothers us. It doesn't have a straight line. So Now, how does this basically impact our equation is that when we look carefully into this equation, okay, the value of V1 right now is being replaced with VBE, and that VBE value will have a specific value of minus 1.5 only at a particular value of temperature and for a given value of VBE. Okay, so basically at these two uh, intersection points, we have this dou VBE with respect to dou T as minus 1.5 millivolt per Kelvin. Okay. Now that when we try to design a circuit which is a combination of both CTAT and PTAT, so the weighing factor that we have here, which is alpha 1 times that of VBE, or in short what we wanted is something like this, right. Um, Still we do not know what is this V2, let me try to explain later. So, when we add these two, combine these two quantities, we have to end up having a result where we end up having a result of 0. Yeah. So, now since because this term that we have here is basically a function of a given temperature and the given value of VB, it is not a constant quantity, and due to which the weighing factor that we add here also has to change depending on the given value of VB. Say for example, if the value of VB is not 750, but rather it is 770 millivolt. Okay. So in that case I have to substitute a different value of alpha 1 rather than the alpha 1 that I have used to evaluate the value uh, of this dou VBE with respect to dou T. Hope that you are clear. So this factor is also has to be varied depending on what value of VBE we are chosen and what value of temperature that we are trying to operate the device. So basically the alpha 1 the choice of alpha 1 becomes more difficult, and the choice of alpha 1 will introduce some sort of error into the circuit, and that error will introduce a non-zero factor here. Okay. So this error happens when we operate the device away from the specific temperature or the specific value of VB for which we calculated this alpha 1. Hope that it is clear for you. Okay. Yeah. So this is some sort of difficulty that we end up having just because of this particular parabolic graph or or this negative temperature coefficient depending on uh, VBE as well as the temperature term. Okay. So just because of these dependency terms, all these difficulties has come into picture. So now what we do is that today we'll start with the discussion of PTAT circuit or a positive temperature coefficient, and later we'll just call whether it is a PTAT or a different circuit. Okay. So in order to exhibit this positive temperature coefficient, uh, let me just give me a time. Just sorry guys, I'm just taking few more time. Yeah, actually written down some notes, but I couldn't able to find it out. But let me just try to explain without that. Maybe I might miss some of the points here. Okay. Yeah. So, in order to discuss about this positive temperature coefficient, it was been discovered in 1960 somewhere. Okay. So, if there are two BGTs that have been operated with unequal current densities, then their differences in their VBEs results in a quantity that is proportional to the temperature. So, what I really mean by this statement is that uh, I have to take two BJTs, and both these BJTs are being operated at completely different current densities or completely different collector currents. Okay. So, let me label this Q1 collector current as n times I naught, and here in this case I am going to assume that the factor beta is equal to 0, which means that the base current is completely equal to 0. Okay. And it exhibits a value of VBE, and let me label that VBE as VBE1. Okay. And let me also try to plug in a current value of I naught into one more transistor having the same emitter area, but through the diode connected structure. Okay. So, let me label this second transistor of BGT as Q2, and it exhibits a voltage VBE as VBE2. Okay. Yeah. So, hope that you are clear with these discussions, and it is a diode connected configuration, nothing fancy about it here. Okay. So, having this kind of structure, uh, just because we know that the collector current in short is defined as saturation current, IS stands for the saturation current, times e to the power of or exponentially related to minus VBE with respect to VT, where VT stands for the value of thermal voltage. Okay. So, one could get down this value of VBE through by just by taking ln on both the sides. One could write this VBE as something like VT times that of ln of IC by IS, and this is the well known expression that we have used even during the discussion of negative temperature coefficient term. Okay. Yeah. So, now just whenever this collector current varies, what happens is that the resultant value of VB will also change. Okay. And those resultant changes is what is being exhibited here, and when I try to observe these voltages as delta VBE, okay, with plus and minus, then one could write this delta VBE as the potential difference between VBE1 minus VBE2. Okay. So, now the expression for this VB1 could be taken out from this above expression. So, let me mark this expression as 3. Okay. So, based on this expression number 3, one could rewrite these VBs in terms of VTs and ln of logarithmic expressions. Okay. Let me try to plug in those things, which one would end up having something like ln of collector current, and let me write the collector current in terms of n times I naught divided by IS. Now, one could see that since the area of the emitter area of both the transistors are same, okay, they result in a saturation current that again tend to have the same result. Okay. So, the saturation current of Q1 as well as saturation current of Q2 basically will end up having same value just because their emitter areas are same. Okay. So, this is something that one has to know, uh, just because we are not talking much more in depth with respect to BJTs, but we are using the BJTs to talk about this BGR. So, in the same similar way, one could write the value of VB with respect to the collector current that is flowing through the device as just I naught. As you could be able to see, the current that is flowing through this Q2 transistor is just I naught divided by the IS, just because the area of this structure is same as that of the area of the Q1 structure. Okay. And just by doing simple math, one would end up having a quantity which is ln of n. Okay. So, Vt into ln of n is this delta VBE. Now, The whole point is that we further have to expand this equation for this Vt. As I said, this Vt is basically is nothing but thermal voltage, which is defined by Kt by Q, okay, where T stands for the temperature term. Now, based on this delta VB, one could see that it is directly proportional to the temperature. And let us see whether this delta VB, which is nothing but our V2 term, exhibits the opposite opposite temperature coefficient or not. Okay, so we already know that this VBE, which we used for V1, exhibited a negative temperature coefficient. Okay, so this term is already known, which we discussed in the last class. But currently, I just need to know whether this delta VBE, which is right now is taken as V2, if it exhibits a positive temperature coefficient. Okay, so we want this to be a positive temperature coefficient. For that, in order to know the temperature coefficient, what we have to do is that we need to differentiate this delta VBE with respect to temperature. So let us try to do that. So when we try to differentiate this delta VBE with respect to the temperature, uh, obviously we have a T term, so which when we differentiate, it goes to a value of 1. We end up having K by Q into this ln term, which is ln of n. Okay, so hope that it is clear till this particular point, and there are a few observations that we just need to make a note from this particular expression. Okay, let me mark this expression as equation number 4, says that we will be using these as our references. Now, currently you could able to see that this delta VB, when we observe, uh, it is completely independent. It's basically a positive quantity, as you could able to see that there is a positive term. This entire quantity is basically results in a positive value. Okay, so as we expected, this delta VB with respect to delta T exhibits a positive temperature coefficient. Yeah, that is done, and it is also observed that it is completely independent of temperature as well as the current, okay, the collector current that is flowing through the device. Okay, so that is something that we need to observe, and based on these two principles, one could plot a Cara, okay, which is VBE with respect to sorry, it is delta VB, it is not VB with respect to temperature, and this Cara would then reflect a straight line. Okay, there is no curvature just because it's just a purely a slope value, which is a constant slope value. Okay, and based on this we would end up having, and based on the factor n, the slope would change. Okay, so probably you will have a very lower slope value depending on the value of n factor here. Okay, so the larger the value of n, you will have a large steep expansion or a steeper graph. Okay, so that's all been said. These slopes are completely a straight line. It results in a completely very straight line. Okay, yeah. So hope these are the observations that we can make out of this, and let us do a simple exercise problems based on this positive temperature coefficient. And since because this delta VB exhibits a constant straight line, the circuit of this delta VB, or basically this particular circuit, we call it as PTAT generator. Okay, just because the delta VB that is generated out of this particular circuit is exhibits a positive temperature coefficient with a constant value. Okay, yeah. So now let us do some simple exercise problem. Let us begin with the calculation. Calculate delta VBE for the circuit shown below. So now in this case, I'm just going to drive those transistors not only with different current densities or different collector currents, but also I'm just going to drive with different areas for the transistors. Okay. So in order to mimic different areas, I could take the Q1 structure being repeated for m times. Okay, so what I really mean is that I'm just going to take individual transistors of Q1 across Q2, the same similar structure of Q1 across Q2, and I'm just going to put all the transistors in parallel, where I have m similar transistors of Q1 being placed in parallel. Okay, so the last transistor can be labeled as Qm plus 1. So the total number of transistors that I have in the second branch will count up to uh, a factor of m, and we know that each of these transistors, when it has an emitter area of Ae, it exhibits a saturation current Is, and since because all these transistors are having an emitter area of Ae, each individual transistors will have Is. Now since all these Is are being combined parallelly, we would end up having a total saturation current as m times Is. Okay, so that is the factor that we have here, just because there are m such parallel transistors are being placed having the same similar emitter area as that of our Q1 structure. Now that we just want to calculate this delta VBE out of this expression. Now we know that the delta VBE is defined as VBE 1 minus VBE2, and one also can recollect that the formula for VBE as let me write the formula for VBE as VT into ln of collector current divided by the saturation current. Okay, so we will use this equation in order to write down these values. Okay, so we have this VT in common, and the collector current that flows through the Q1 transistor is n times I naught, and the saturation current is just Is, and again we have this VBE2, which is the potential across each and every structure will be the same. So due to which one could write it as Vt into ln of the collector current that flows through the entire structure. If I observe that this entire m transistors as a single transistor, then the total current that flows through the device would be just I naught collector current, and whereas the saturation current is nothing but the m times that of Is. Okay, so this is the case when we have assumed that all the m transistors have been combined into a single structure, then one could visualize this current flow through this entire second branch m transistors as something like this. Okay, so having done with this, the math is pretty simple after this. So we can just pull out this term Vt in common, and we can cancel out some of the common terms, and when we do all this math, we would end up having something like this. Okay, so Vt into ln of n times that of m. Okay, so the m is basically the m number of transistors, and n is nothing but it comes through the different current flows through the collector currents of Q1 and Q2 structure. Okay, so hope that writing this expression is pretty straightforward. Okay, so this is the equation number 1, and let us do a second example. Let us assume two transistors which are BJTs uh, that are being biased at current density ratio of 10:1, operated at a temperature of 300 Kelvin. Okay, now there are two parts in this question. The first part being what is the difference in their BJTs, sorry, in their VBEs, and what is its temperature dependency or dependence. Okay, so So once we answer these two questions, we'll just move on to the discussion of BGR, but uh, solving this problem will give us some sort of idea for us. Okay, so in this case we have to assume two BJTs that have been supplied with two different current densities as a ratio of 10:1. Okay, so in this case the factor n denotes a value of 10. Okay, that's the only thing. Now based on the previous discussion or based on the circuit that has been drawn, okay, so one could utilize this circuit in order to evaluate it, and we know that this equation could be could result in an expansion, that is delta VB is equal to Vt times that of ln of n. Okay, so I am just going to use the same expression in order to write down this result. Okay, so the difference in their VBs, which is VBE1 minus VBE2, okay, which is equal to Vt into ln of the ratios of current collector currents. Okay, so let me write it as IC1 by IC2 here. Okay, assuming that both the transistors, so in this case the transistors are assumed to have the same areas, okay, emitter area, so which means that the IS1 would be equal to IS2, so it says that it get cancelled out. Okay, and one can even write this collector currents as something like, in terms of current densities, as something like collector current. Okay, so here in this case the JC term represents the current density, and that when it is being multiplied by the area would end up resulting in a current which is defined as a collector current. Okay, so hope that this notation is pretty simple. Okay, so nothing fancy about it. So this has a unit of amperes, whereas this one will have a unit of amperes per meter square, and when we multiply this with the meter square we end up having an ampere. That's the only thing. Okay, yeah, so this factor or the ratio of IC1 by IC2 can also be written in terms of densities, is what I try to mean here, okay, as JC1 by JC2. Yeah. Now this is the ratio that has been given here or been stated in the question as 10:1. So one would end up having this delta VB is proportional to Vt into ln of 10. Now one could also expand this Vt term as Kt by Q and to ln of 10, and writing the values of K as 1.38 into 10 to the power minus 23, and the temperature at which we are operating is basically 300 Kelvin. So let me write it as 300 divided by the charge of electron, which is 1.6 in 602 into 10 to the power minus 19. Okay. Yeah. So and that the whole of these things has to be multiplied with ln of 10. Okay. So when you do this math of substituting all these values, one would end up having a value of delta VBE which is equal to 59.5 millivolt. Okay, and this is the value that I am getting for a temperature that is equal to 300 Kelvin, and for the n factor that is equal to 10. Okay, so this is more important. So it basically defined only for these two factors. Okay, yeah. So having got this as our first result, our the computation of first one is done. The differences in the VBs are being done. Now let us move on to the second part of this question, and what we have asked is that what is the temperature dependency. Now what we really mean by this the temperature dependency is that when this temperature rises by 1 Kelvin, how much is the value of delta VB changes, okay, and that is what we mean by this temperature dependency. Now in order to evaluate such a quantity, let me write this new value of delta VB as VB prime that has been evaluated not at temperature that is equal to 300, but evaluated 1 degree above this 300 Kelvin, which is nothing but 301. Okay. In order to evaluate that, one could use this result itself. Okay. The value of delta VB at 300 Kelvin can be used in order to evaluate the new value of delta VB, which is evaluated at 300 or 301 Kelvin. Okay. Yeah. So having said that, it's a simple math. So the only thing is that we just need to substitute the value of delta VB which was evaluated at 300 Kelvin that we need to use and multiply it with the temperatures. So, at the top we will be using this 301 which is what we wanted, and at the bottom we will be using this 300 kelvins. Okay. So, this particular factor or this particular expression would give us the value of delta VB at 301 Kelvin. Okay. So, the final result of this would then be manipulated just by the simple calculation, and the final result is 59.7 rather than 5 millivolt. Okay. This is the new value of VB when the temperature rises by 1 Kelvin. Okay. Now, and in order to evaluate this temperature coefficient or the temperature dependency, we just need to evaluate this factor, which is delta VB with respect to temperature. And the quickest way to do this manipulation is by using the value of either this or this. Okay. So, let me use this, which is 59.5 milli. Differentiation is nothing but the ratio of delta VB evaluated at that temperature, which is 300 Kelvin. Okay. So, that is what I have done. Okay. And so, this ends up having a result which is equal to 0.198 millivolt per Kelvin, and this is the temperature coefficient resulting in a positive value. Okay. And this is the case when we have the factor of n that is equal to 10. Okay. So, it is not for any other different factors. This is the only thing that I always have to emphasize, that whatever the value that we have computed as 59.5 or 59.7, okay, all these values are evaluated assuming that the ratio of or the ratio of current densities are taken as 10. Okay. So, in this case, if we have a different value of n, then these values would change automatically. Okay. And even the slope value will change automatically. So, now that we have both these quantities, and we found that even this temperature coefficient end up having a positive result, we have this delta VB giving us a positive temperature coefficient, and we have this just VBE which exhibits this negative temperature coefficient. The only thing that we are ending up we are yet to do is the addition of these two quantities in order to create what is known as temperature independent reference circuit. Okay. Yeah. So, for that we just need to combine these two factors, okay, in order to evaluate that. So, basically first let me draw this combination. So, we just need to add both these circuits in order to create a V reference circuit, and this V reference circuit